graph theory, some questions of graph theory. In the last two sessions, we have discussed many questions from mathematical logic. And in this graph theory, I just want to tell you that this is not a beginning course. The graph theory we have already studied. Okay, so in in Gate Forum, I have already taught the complete discrete mathematics and this graph theory. So in a very detailed discussion, I have completed this graph theory. So if you want, then you can access this discrete mathematics course from Gate Forum course website. And in this lecture, what I am going to do, I am going to discuss some questions, some tricky concepts, some tricky questions from graph theory. So let's discuss. Now, before we proceed, let me just give you a quick revision, a very quick revision of this graph theory. Let me give you. So first of all, what is a graph? Now, a graph, remember in our normal mathematics till 12th class, okay, in general mathematics, our graph look like this. Like this is the sine, something like this sine graph, cos graph, okay, and this like this e power x, e power minus x, and so on. So these are the graphs that look like. But in discrete mathematics, what is the graph? Graph is normally some set of nodes and some set of edges. So basically, for example, let's assume this is a node A, node B, node C. So we have three nodes and some edges which are connecting these nodes. For example, this A and B, these are connected via this edge. So this edge can be called AB edge because this is connecting vertex A and vertex B. So these are vertices, these are edges, and this complete you can say structure. This is called graph. So a graph is nothing but some set of vertices and some set of edges. These edges are connecting these vertices. Okay. Now, in graph theory, we have many concepts, and today I will. And all these concepts I have already discussed in the Gate Forum Discrete Mathematics course. There I have already discussed all these concepts. But let me discuss few important concepts from the Gate point of view, or from any exam point of view. There are some concepts which are very frequently asked. So one of those concepts is handshaking lemma. This handshaking lemma is one of the concepts which is very frequently asked. You can just solve the previous year questions of Gate exam from the graph theory. You will see that this handshaking lemma is very frequently asked concept. Now, what is this handshaking lemma? Before we see this handshaking lemma, let me tell you what is degree of a graph. So if you have any graph, let's assume this graph you have A, B, C, D, and so these are the four vertices you have. And let's assume this graph looks like this. So this complete structure is a graph. Let's call it graph G. You can see what are the vertices? A, B, C, D. These are the vertices, and we have three edges. This edge is connecting A and D, this edge is connecting A and C, and this edge is connecting C and D. Now this is your graph. In this graph, what is the concept of degree? The concept of degree is very simple. The number of edges incident on a vertex, that is degree of a vertex. For example, here, this A, on this A, there are two edges that are incident, this edge and this edge. So we can say degree of vertex A is 2. This vertex B, if you see, there is no edge that is incident on B. So degree of this vertex B is 0. The degree of vertex D is 2, and the degree of vertex C is 2, because you can see that on this vertex C there are two edges that are incident. Okay, this edge and this edge. So this is the definition of degree. Degree of any vertex is nothing but number of edges incident on that vertex. Okay. Or if this is a simple graph, what is a simple graph? Simple graph looks like this. Like this is a simple graph. Okay. And we have some other type of graphs also. For example, pseudograph, multigraph, and many other class of graphs also we have. But in discrete, like most of the time, almost 99% of the time, in graph theory we deal with simple graphs like this. Okay, these are the simple graphs. Anyway, now so this is the concept of degree. Once we have this concept of degree, let's see what is this handshaking lemma. This handshaking lemma, first let me tell you the statement of this handshaking lemma, then I will tell you the proof. So the statement is this: assume you have a graph v comma e. This is set of vertices, this is set of edges. This is your graph. Then handshaking lemma says that the summation of all degree, sum of all degrees, that is equal to twice the number of edges. Number of edges. This is your handshaking lemma. Okay, summation of all degrees that is equal to twice the number of edges. Now this is the handshaking lemma, and this is very important. This is a simple theorem and this is a simple result, but this is very 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 much important, and we will see the proof of it. Let's see how we can prove it. See, you need to observe what is the degree. Let's assume you have a vertex A, vertex B. Assume these vertices are not connected. These are not connected. Okay. At this point of time, let's assume that this A is connected to some other vertices, this B is connected to some other vertices. So assume that the degree of vertex A, that is, let's assume M, and the degree of vertex B is N. Let's assume. So this is the degree of vertex B, and this is the degree of vertex A. Now if I add one more edge, like if I connect A and B, let's assume after this situation, what I do, after this situation I connect A and B. All the things are same, but I am putting edge between A and B. This additional edge I am putting. Now what will happen? See, already the degree of vertex A was M, means there were M edges that were incident on A. These were basically M edges, you can say. Okay, and these were basically N edges by the definition of degree. Now if I add another edge, then what will happen? So if I add this another edge, then the degree of this vertex A, this will increase by 1, because you can see this edge, you can see if I add this edge, then already M edges were incident on A. Now one additional edge is incident on vertex A. So the degree of vertex A is increasing by 1. Similarly, there let's come to this vertex B. There were already n edges that were incident on B. Now, after adding this edge, the number of edges that are incident on B, that will increase by 1. So you can see the degree of vertex B is increasing by 1. The degree of vertex A is increasing by 1 by addition of this edge. So what you can observe, that when you add an edge, means this edge will basically will increase the degree of its end vertices. This A and B, these are the end vertices of this edge. This is your edge, this is connecting A and B. So this edge will increase the degree of A by 1 and degree of B by 1. So total degree, if you see, total degree means this degree is increased by 1, this degree is increased by 1, so total degree is increased by 2. That is the point. Okay, now you can say that this age, every age basically contributes a summation of 2 in the sum of degree. So that is the point, every age will contribute a summation of 2, you can say, because summation of 2 in total degree. If you see, if you calculate the total degree, then this age will contribute a summation of 2, because the total degree is increasing by 2 because of this age. So that is the point. Now you can just very easily say that this is the proof, and you can say that basically every age will contribute a summation of 2 in the total degree. So that's why the total degree will be equal to twice the number of edges. Because of each age, if you have, let's assume you have 10 edges, then every age is contributing 2, every age. So 10 edges will contribute a summation of 20. So if you have 10 edges, then what will be the total degree? Total degree will be 20, because every age is giving you a summation of 2, so these 10 edges will give you 20. So that is the point, and this is your degree sum formula. Also, like, what is total degree? Total degree means you add the degree of all the vertices. For example, let's take this graph: A, B, C, D, E, F. Let's take this graph. Now in this graph, the degree of vertex F, what is that? The degree of vertex F is A, 1. Because on F, there is only one edge that is incident on 1. The degree of vertex A, that is 1. Degree of vertex B, that is 3, because of these three edges. The degree of vertex E is 3, and degree of vertex C is 2, degree of vertex D is 2. So what will, this is the individual degree of each vertex is like this. But what is the total degree? Total degree means you add all the degrees, means 1 plus 3 plus 3 plus 1 plus 2 plus 2. This will be the total degree. You can just check it out. What is this value? If you add this, then the answer will be 12. And this is nothing but twice, sorry, what is this value? Let's see, 336, and this is your 8, yes, 12. So correct. Now you can see this is your 12. And what is the number of edges? Number of edges is 1 2 3 4 5 6. There are 6 edges. So you can see this total degree is equal to twice the number of edges. Number of edges is 6. So this is the point, and this is your degree sum formula. This is called handshaking lemma, or this is called degree sum formula. So this is the degree sum formula. If you have any graph, there are, let's assume in this graph there are m edges, then the total degree of all the vertices, the total degree, that will be equal to twice the number of edges, because every edge contributes a summation of 2. Every edge increases the total degree by 2. That is the point. Now, after this point, we can see this simple corollary. Let's see this result. He's saying that in every graph, the number of vertices of odd degree is even. You can have any graph, whatever graph you will have, the number of vertices of odd degree, that will be even. What it is saying? It is saying like this. Again, let's take this example: A, B, C, D, and let's assume this is your graph. In this graph, you can see the degree of A is 2, degree of B is 2, degree of D is 2, degree of C is 3, and degree of E is 1. Now, you can see this is even degree, this is even degree, this is even degree, this is odd degree, this is odd degree. So how many vertices are there of odd degree? This is odd degree vertex, this is odd degree vertex. So two vertices have odd degree, you can say. Two vertices have odd degree. Because two vertices have odd degree, you can see. So you can say number of vertices which have odd degree, that will be 2. And 2 is an even number. This is our statement, you can see. Because the number of vertices of odd degree, the number of vertices which have odd degree, that number of vertices will be even. Okay, so let's prove it. You can prove it very easily from the handshaking lemma, or this degree sum formula that we have seen. What we have seen? We have seen that total degree is basically equal to twice the number of edges. Let's assume this m, this is the number of edges. Now, this total degree, you can see that you have any graph G, then in this graph G, either you will have an even degree vertex, like you can say that your vertex will either have even degree, or your vertex will have odd degree. This is possible, either even degree or odd degree. So what you can say, this total degree you can divide like this: total degree of even degree vertices. What you can say? You can say total degree of even degree vertices. Means you take all the even degree vertices and you add their degree. Okay, and you can say that total degree of odd degree vertices. So this is how you can: total degree of odd degree vertices. You take all the odd degree vertices and you add their degrees. Now, this is equal to twice the number of edges. Now, one thing you can see, this is, what is this? This is total degree of even degree vertices. Means you take all the even degree vertices. This is even degree vertex. This is even degree vertex, and you add their degree. So this is even. This is even. This is even, because these are even degree vertices. So the degree is even. So if you add all the even numbers, then this will be an even number. We know this is an even number. Okay, and we know this is also even number because this is twice the number of edges. So that's why this is also even number. So if this is even number, then automatically this has to be even number. This has to be even number. Now this has to be even number. And what is this? This is total degree of odd degree vertices. So means, let's assume these are odd degree vertices. Let's assume you have let's assume this is vertex A, vertex B, vertex C, vertex D. These are odd degree vertices. Means it has degree odd. Okay, and it has degree odd, it has degree odd, it has degree odd. So their summation, this summation must be even. Means odd plus odd plus odd and so on plus odd. If you add all the odd degree vertices, if you do the summation of degree of odd degree vertex, then that should be even. So what should happen? It should happen that number of odd degree vertices must be even, because you know odd plus odd is even, even plus odd is odd. So that's why the total number of odd degree vertices, okay, the total number of odd degree vertices must be even. So this is a very simple result. This is how you can prove it. So this is now, so this is done, this is done, and these are important theorems, these are important results. Now let's see this question. He's saying, prove that if a graph has exactly two vertices of odd degree, then they are connected by a path. Now use like this question is application of degree sum formula. We have seen these two things. Now this question is just an application, like how can you apply this degree sum formula. Let's read this question. What he is asking? He is asking us to prove that if a graph has exactly two vertices of odd degree, exactly two vertices of odd degree, then they are connected by a path. Now we can prove it very easily. Assume that this is not true. For contradiction, see, he is saying that you have a graph, and this graph has exactly two vertices of odd degree, exactly two odd degree vertex, he is saying. And now he's saying that these, let's assume these exactly two odd degree vertices, let's assume these are a comma b. So this is odd degree vertex, this is odd degree vertex. Now he's saying that then we have to prove that they are connected by a path. Means this a and b, these are connected. From a I can go to b. You can see, for example, consider this graph a b c, consider this graph D. In this graph, you can see that we have path from A to C, because from A I can go to C. From C I can go to B. Let's assume I am at C. Now I can go to B, because I can take this edge, then I will reach here, then I can take this edge. So this is the path from B to C. But how can you go from A to D? Like you are at A, you are standing here, and you want to go to D. You want to go to D, you want to go to here, but you cannot go because there is no path. Okay, from A you can go to C, you can take this edge. From A you can go to B, but from A you cannot go to D. From A you cannot go to E. So this is a disconnected graph. This is disconnected, you can see. Okay, here you can say there is a disconnection. Now you can say that there is no path from A to D, there is no path from A to E, there is no path from B to D, there is no path from B to E, and so on. Now in this question, he is saying that if you have exactly two vertices of odd degree, then they must be connected. So we can prove it by contradiction. For contradiction, we will assume that these two vertices are in different components. Means this vertex A is here and this vertex B is here, and there is no path. Means they are disconnected. Now, if this is happening, then remember this is also a graph. See, this is also a graph, right? This is a smaller graph, you can say. This is also a graph, and this is also a graph. Like this is also a graph, this is also a graph. So for this graph, it should apply, what should apply? This theorem should apply. This, in every graph, the number of odd degree vertices must be even, so this should apply. Means, but you can see in this graph there is only one odd degree vertex. Means number of odd degree vertices in this graph is odd, because there is only one odd degree vertex. So that's why you can say this cannot happen, because we have proven that in every graph the number of odd degree vertex must be even. So this cannot happen. Similarly, this cannot happen. So what you can say? You can say that it cannot happen that this A and B, these are in like they are disconnected. It cannot happen. So this is how you can prove. Hence we can say that if a graph has exactly two vertices of odd degree, then they are connected by a path. Okay, they will definitely be connected. This A will definitely be connected by B. Okay, so this is how you can very easily prove it. This is just application of degree sum formula. This is our degree sum formula. Let's see this next application of degree sum formula. One more application, let's see. Now we have a result and we will prove this result. What he's saying that in any binary tree, whatever binary tree you take, in any binary tree, in any binary tree, he's saying that the number of leaves that is equal to number of degree 2 vertices, degree, you can say I can say like this, vertex degree 2 vertices plus 1, number of degree 2 vertices plus 1. So this is the result. In any binary tree, the number of leaf nodes will be equal to number of 2 degree vertices plus 1. Like you can see that, let's assume this is your graph, this is your tree. Let's assume A, B, C, C, D, E, and you can see F, G. Let's assume this is your tree. Now in this tree, okay, this is a rooted binary tree. In any rooted binary tree means this is a root node and these are the children. Like this B comma C, these are the child of A. This D comma E, these are the child of B. F comma G, these are the child of E. So this is a rooted binary tree and this is the root node. Now in this tree, for example, you can see this vertex has two children. This vertex is leaf because it has no children, you can say. So this is your leaf node and this is your two children node. This vertex has two children. Okay, so let's define degree. The number, the what is degree? I told you degree means number of edges incident on this vertex. So it has degree 2, you can see. Okay, anyway, similarly this vertex B, you can see this vertex B, it has degree 3. This, so degree is 3. Okay, and this vertex E, it has degree 3. So this is leaf node. So this is the point, you can see. Okay, let's assume there is another node, that is M. You can see this is 1 degree this vertex has only one child. This vertex D, it has only one child. So but anyway, the degree of this vertex is 2. The degree of vertex D, that is 2. So this is how basically this is some terminology we have seen: root node, leaf node. Okay, what is the degree and all these things we have seen. And what is the children? It has two children, it has one children. So that is the point. Now he is saying that in any rooted binary tree, number of leaves must be equal to number of two this is your number of two children. I should say that number of vertices having two children. This should I should say that. So this is the statement. Let me rewrite it. This statement is this: number of leaves is equal to number of number of vertices having two children plus 1. Number of vertices having two children plus 1. So this is the result that we need to see. You can very easily, you can verify. Okay, before we prove it, you can verify. This has two children. So okay, this has two children, this has two children. So how many vertices we have which have two children? So the two children vertices are 3. Okay, 3 vertices have two children. Now what is the number of leaves? This is leaf, this is leaf, this is leaf, this is leaf. So how many leaves you have? Total 4 leaves you have. And you can see 4 is equal to 3 plus 1. Very easily you can see. So now let's prove it. We have verified it. Very easily you can verify it. Now let's prove it. So to prove, what we will do, we will use the degree sum formula. The same thing we will do. Because this is let's assume that this tree has n vertices. Assume it has n vertices. So this tree, okay, n vertices in tree. Now you know that this is a binary tree, this is a rooted binary tree. So what this n will be? This n will be basically n0 plus n1 plus n2. Remember what is n0? N0 means leaf node. N1 means the number of nodes which has one child. N2 means number of nodes which has two children. So this N2 means this is a N2 because it has two child. So this is a two children vertex. Hence, what is this N2? This N2 is basically, you can say, number of vertices having two children. Or N1 means number of vertices having one child, and N0 means number of vertices having zero child. Means these are the leaves, number of leaves, you can see number of leaves. So this is one equation, you can say n equal to n0 plus n1 plus n2, because in a binary tree either you have leaves, or you have vertices which has two children, or you have vertices which have one child. So this is the point. Also, this is a tree, so you can say that number of edges. Let's assume that the e is the number of edges, this is number of edges, so this will be equal to number of vertices minus 1, because in a tree what happens, in a tree number of edges is always equal to number of vertices minus 1. So this another equation we have. Now one more equation you can make from degree sum formula. Degree sum formula says that the summation of all degrees, total degrees, that should be equal to twice the number of edges. Now you can see these many vertices have these vertices have degree 1. Every leaf has degree 1, because if this is a leaf, then this has degree 1 because there is one edge incident on this leaf. So these many vertices have degree 1 plus. Now let's talk about this vertex which has these vertices. So like, so this degree, okay, one child vertex, let's assume this is a vertex you have and this has one child. Okay, so what will be the degree of this vertex? The degree of this vertex will be basically 2, because okay, it is also children of some other node. So you can say you have n1 multiplied by 1, n1 multiplied by 2. This is your, remember I am not talking about root node, because this root node, even though it has two child, let's assume that it has two child, let's assume, then also the degree of this root node will be 2. So except for root node, okay, I will write about this root node at the end. Right now I am assuming that these are known root node, these are also known root node. So now you can see, now here let's come to this n2. In this n2, you can see I am not including the root node. Okay, in this n2 I am not including the root node, so n2 minus 1, okay, plus, wait a second, so what I am saying, this root node, wait a second, so what we are saying, that this degree is equal to number of leaf plus 3d2. Okay, and what is this? With exactly two child and with exactly one children, this is d1, and you need to subtract from this, you need to subtract 1, right? Yes. So okay, yes, sorry for that. So let me just rewrite it. Let me rewrite these equations. Yeah, so you can see first equation that we have is n equal to n0 plus n1 plus n2. This is the first equation. The second equation is number of edges is equal to number of vertices minus 1. This is the second equation. And the third equation is basically degree sum formula, means summation of all degrees. So these vertices, n0 vertices, they have degree 1, plus these vertices, these n1 vertices, they have degree 2. Okay, and these n2 vertices, they have degree 3. But remember, let's focus on this root node. If you focus on this root node, then you can see that if this root node is, let's assume it has two children. If this root node has two children, then still its degree will be 2. But you can see all other two child vertices, they have degree 3. For example, let's assume this is a node which has degree which has two child. Then you can see the degree of this node will be 3. So degree of this node will be 3, but this root is also having two children, but the degree of root is 2. Similarly, you can consider this situation. Let's assume this root node has only one child. Okay. Now let's assume that because this has one child, okay, so you can see this is in the category of n1 because this root has only one child, but the degree of this root still is 1 only. So you can see that this root node always has whichever category it belongs to, whether this root node belongs to this n2 category or whether this root node belongs to n1 category, to whichever category this root node belongs, you can see that it always has 1 degree less, like 1 degree less. Okay, whichever category, from that category it will have one less degree. So that's why we need to subtract it. We need to subtract -1 because of root node. So this is because of root node. Now this finally, and this equation, this is your total degree and this is equal to twice the number of edges. This is equal to 2e. So you can say basically n0 plus 2n1 plus 3n2, that is equal to 2e plus 1. And what is 2 and what is e? You know e is nothing but n minus 1. So 2 into n minus 1 plus 1, that is 2n plus 1. 2n minus 1, so that is 2n minus 1. And this is equal to, and let's assume the number of leaves, because these are the leaves, so number of leaves is l. Now plus, so plus 2n1 plus 3n2, and you can put this n is equal to n0 plus n1 plus n2, so you can put it l plus 2n1 plus 3n2 is equal to, you can put it here, value of n, so it will be 2l plus 2n1 plus 2n2 minus 1. So 2n1 is cancel out, and this, you can say that this l will cancel out this, and this 2 and 2 will cancel out this 3. So finally what you have n2 is equal to l minus 1. And this is what we, this is the result that we were looking for. Anyway, this is the proof, very easy proof. We have only made 3 equations. This is the first equation, the total number of vertices, this will be equal to number of leaves plus number of one child vertices plus number of two child vertices. This is the first equation. The second equation is, in every tree number of edges is equal to number of vertices minus 1. This is the second equation. And this is the third equation that we have made from the degree sum formula. The total degree must be equal to twice the number of edges. But here there was a catch. There was a trick here. This root node, whichever category it belongs to, if this root node belongs to the two child category, then also it will have one less degree, because normally all other two children vertices, they will have 3 degree, but this root node, this will have 2 degree. Similarly, if this root node belongs to this n1 category, means this root node has one child, then normally all other one child vertices, if you see normally, then they will have 2 degree, but this root will have 1 degree. So that is the reason that this root node, it has one less degree, so that's why we are subtracting it. Okay, whichever category this root node belongs, this will have one less degree, so that's why this is the subtraction that we are doing. And finally this is equal to twice the number of edges, and then we are just using these equations, these 3 equations we are using to get this result. So this is a nice result, and many gate questions are based on this result. The reason why I am talking about this result, because there are many questions in previous year gate exam which are based on this result. Okay, also let me tell you one more thing here. When we talk about a graph, here you can see that when we talk about any graph, then there the degree is fixed, because the degree is basically number of vertices incident on that graph. Okay, for example, here you can see the degree of this vertex is 2, the degree of vertex is 1, the degree of this vertex is 1. And every tree is a graph. If you talk about every tree, then you can see this is also a tree, you can see. And every tree is a graph, so it has the same concept. It has degree 1, degree 1, degree 1, degree 4, degree 1. So you can see, because every tree is a graph. But when we go to rooted tree, when we discuss about rooted tree, then sometimes some authors, not all but some authors, what they do, they define degree in terms of number of children. So that is a conventional thing. Remember, some authors, what they do, so some authors do this, so I can say some authors, they do like this. and other authors. Some authors do this and some authors do this. What they do, let's assume this is a vertex and it has two child. Let's assume this is the situation. Now some authors, what they will do, they will use the same terminology. They will say that this has degree 3 because there are three edges that are incident on it. So they will say that this is degree 3. But there are many other authors also, many standard, some authors, what they do, in a rooted tree, remember, in a rooted tree they define degree in terms of number of children node. Means they, what they will say, they will say that this vertex has degree 2. So this is a conventional thing that you need to, like you need to take care. So even though in gate exam they must specify, in gate exam you will see they always specify what is the meaning of degree when they talk about rooted tree. If they are talking about rooted tree, then they will define what is the definition of degree they are using, whether they are using this definition or whether they are using this definition. But anyway, this is some students, what they do, they waste significant amount of time because of these things. They say that, like some student is saying that this vertex has degree 2, then some other student, he will argue that this vertex has degree 3. They both are correct. He is also correct, he is also correct, because in rooted tree the definition of degree, that is not universal. Some authors use this definition and some authors use this definition. So that's why this is a conventional thing. In gate exam you don't have to worry, they will specify what is the meaning of degree when they ask you about rooted tree. If they are asking you about general tree, then you need to use the same definition, because every tree is a graph. So this is a small thing. Okay, this is the proof. Okay, this is the proof we have seen. Now let's see the next question. Try this question. He's saying that suppose that G is a simple graph on 10 vertices that is not connected. He's saying that this graph is not connected. Prove that G has at most 36 edges. Maximum 36 edges will be there. He's asking, can equality occur? Means can we have 36 edges? So this is the problem. Okay, let's prove it. Let me prove it. Okay, let's solve it. Basically, how to solve this question. He's saying G is a simple graph on 10 vertices and this is not connected. Not connected means this is basically disconnected. Means we have like this and we have parts. Okay, we have two parts. But he is asking how many at most edges I can have. G has at most these many edges, means maximum how many edges I can have. So if I want to have maximum number of edges, then what I will do, I will make only two partition. Like I will do like this, one partition, another partition. Okay, so this is called component. We will say that this is one component, this is another component. Now he is asking how many maximum edges you can have, maximum number of edges you can have. So what you can do, see, many different partitions you can do. Maybe you can put only one vertex here, 9 vertices here. Maybe you can put 2 vertices here, 8 vertices here, 3 vertices here, 7 vertices here, 5 vertices here, 5 vertices here. Okay, 4 vertices here, 6 vertices here. So there are many different disconnections are possible. You can see this is disconnected here, 6 vertices here, 4 vertices here, 9 vertices here, 1 vertex. So different possibilities are there. Now which of these possibilities will give us maximum number of edges that we want to find out? Which of these possibilities will give us? So to solve this, let's assume that what you are doing two component you are making. Let's assume there are number of vertices here is a. So this is a here, then automatically there will be 10 minus a, these many vertices, because total number of vertices is 10. So if a vertices are here, then 10 minus a vertices will be here. Now what you want to do, you want to make maximum number of edges. So what we will do, we will put maximum number of edges here, we will put maximum number of edges here. Now to make maximum edges, what we need to do, we need to make complete graph. Complete graph means, let's assume you have 3 vertices, then you connect all these vertices. Complete graph means every two vertices are connected. So this is what we will do, we will connect every possible pair of vertices. So If you do like this, then how many edges you can have? You can have nc2, these many edges you can have, because from out of n vertices, let's assume you have n vertices, then out of n vertices you will select every pair of vertex, means n choose 2. N choose 2 means from n vertices you will select every pair of two vertices, and between those vertices what you will do, you will add edge between every pair of vertices. So hence you can say there will be nc2 edges. Okay, if you have a vertices, then there will be ac2 edges, and if you have 10 minus a vertices, then you will have these many edges maximum, because we want to make maximum edges. He's asking us maximum edges, so this is the maximum number of edges that are possible. Now what is this ac2? ac2 means a minus 1 by 2 plus, what is this? This is your 10 minus a, 10 minus a minus 1 by 2, and now you can just add them. Now what you will get? You will get a square minus a plus, what is this value finally? Okay, this value you can just calculate. Okay, let me calculate it. 100. Okay, then minus 10a and minus 10 minus 10a and plus a square and plus a. So this is what you will get. Now from this you can see this is minus 10a, minus 10a means minus 20a, and minus 20, and this is minus 21a. So this a will cancel out. So basically minus 20a you have, minus 20a you have, this is a square, this is a square, so 2a square you have, and this is your 100 minus 10, so that is 90 you have, divided by 2. So this is what you have. Finally if you divide by 2, then what you will get? You will get a square minus 10a plus 45. This is what you will get. Okay, a square minus 10a plus 45, a square minus 10a plus 45, this is what you will get. This is the number of edges, this is the number of edges, and we are assuming that here we have a vertices, and we are assuming that here we have 10 minus a vertices, because total number of vertices is a, total number of vertices is 10. So we are assuming this. Now this is the number of edges that we will get. This is the number of edges. We want to maximize it. I told you, because we can have different partitions, maybe 5 vertices here, 5 vertices here, or maybe 9 vertices here, 1 vertex here, or maybe 8 vertices here, 2 vertices here. So we can have different partitions. So which partition will give us maximum number of edges, that we need to find out. So this we want to maximize, this value we want to maximize. So again, what we can do, we can use the maxima minima principle. So for which value of a, for which value of a this will be maximum, so for that you can differentiate it with respect to a, means you can do like this dda, and this a square minus 10a plus 45, what it will be? It will be 2a minus 10. So this, in the maxima minima, I hope that you already know those concepts. So what we do, if we want to find maximum or minimum value of any function, this is a function, if you want to find out maximum or minimum value, then what you need to do, you need to put it equal to 0. So from here you will get a equal to 5, but remember we need to see whether this a equal to 5 will give us maximum or minimum. We don't know whether this will give us maximum or whether this will give us minimum. So what we will do, we will double differentiate it, means we will again differentiate dda of 2a minus 10. So if you do the double differentiation, you will get 2, and this is a positive value, this is greater than 0. Because this is greater than 0, so you can say that this will give us, this a equal to 5, this will give us minimum, because this is this double differentiation is greater than 0. So this a equal to 5, actually this will give us minimum. Hence on this a equal to 5, when you do this a 5 comma 5, this will give us minimum number of edges. Sorry, yeah, this basically will give us minimum value of this equation, but we want to find out the maximum value of this equation. Now you can notice one thing, a square minus 10a plus 45, this is our equation, and we have already seen that this 5 a equal to 5, this will give us minimum value of this equation, and this is a quadratic equation, so its graph is like this, either this or this is the graph. But you can see the the coefficient of a square, that is positive, so it will be graph like this. it will be a graph like this. So if you make this graph, and this is the minimum value, means this a equal to 5 is here because this is the minimum value, so your graph will go like this, something like this. And here it will go minimum. So you can see this graph is increasing here also, this graph is increasing here also. So the value, the maximum value that you will get, where will you get the maximum value? Get you will get in the corner, because this a can be from 1 to 9. Okay, you know this a vertices are here, 10 minus a vertices are here. So this a either can be 1 or this a can be 9. This is the range. Okay, so maximum value you will get when a is equal to 1 or 9. You can say a equal to 1 or a equal to 9 will give you maximum value of a square minus 10a plus 45. And what is that maximum value? That maximum value you can put either this or you can put this. So you will get 1, you can put 1, then 1 minus 10 plus 45 is equal to, that is 36. So this will be the maximum number of edges. Hence answer will be 36. This is what he was asking. He was asking that G is a simple graph on 10 vertices that is not connected. Then prove that G has at most 36 edges. So we have proven that if you have a disconnected graph, total 10 vertices, and you have a disconnected graph, then maximum you can make 36 edges. This is the maximum you can make. So this is the point and this is the proof. Like some students, they might have not got it, they might have found it hard. This is not hard, just we have used the concept of maximum minima. We assumed that this partition has a vertices, then automatically this partition will have 10 minus a vertices. Then we are making it complete graph so that we can have maximum edges. We are also making it complete graph so that we can have maximum edges. So the number of edges here will be AC2, number of edges here will be 10 minus AC2. Now we are adding it. Then we will get this equation. This equation we will get. We want to maximize this equation because this equation is nothing but number of edges. We want to maximize number of edges. So for that I am doing the differentiation. If I do differentiation, then I will get a equal to 5. But I don't know whether this a equal to 5 is minima or maxima. I don't know. So that's why I am doing double differentiation. Double differentiation will give me 2, which is greater than 0. So that's why I know that this is minima. Now, because this is minima and this is a quadratic equation always has this type of graph, either this type of graph or this type of graph. Okay, but you can see like how to decide whether this graph or this graph, that you can decide from the coefficient of a square. The coefficient of a square is positive, so that's why the graph will look like this. Okay, and because the graph looks like this, and in this graph you can see, if your graph is like this, let's assume your graph is okay, your graph is like this, then you can see this is the minima, and this minima is your x equal to 5, a equal to 5. This is the minima. So if you go this side, then you will basically, it will increase. But this a has this limitation that this a either can be 1 or this a can be 2, 3 and so on. This a can go from 1 to 9. So we can say that maximum value will come on either 1 or 9. Hence we are putting a equal to 1, or you can put a equal to 9. This will give you maximum value, and the maximum value will be 36. So number of edges, maximum number of edges will be 36. So this is just a simple concept. I have seen many students actually, they directly solve this question without knowing this maxima minima, and without doing all these things. They directly solve it because they have by hearted. They have already by hearted that if you have disconnected graph, let's assume the disconnected graph, then they have already by hearted that if you want to make maximum number of edges, then what you need to do, you need to put one vertex here and remaining vertices here. Then you make it complete graph. So like this, now you make it complete graph. So because you have 10 vertices, so what you do, you put one vertex here, you put 9 vertices here. Now you make it complete graph. So how many edges will be there? Number of edges will be 9c2, and that is nothing but 9 into 8 divided by 2, that is nothing but 36. So many students, they directly answer it, like they will take only half a minute, maybe half a minute they will take to answer 36, and they will feel proud. So the point is that they don't know from where, how, like they don't know the why they are doing this. They don't know, they have by hearted it. They have by hearted it that okay, this is what happens, this will give us maximum, so they will do like this. But I just wanted to give you the proof so that you know how these things work. Many different concepts, how they can come together. Like in this one question, we have applied the concept from calculus, we have applied the concepts from graph theory. So this is how different subjects will come together. Now we will also see one question in which we will apply the concepts of graph theory plus the concepts of dbms. So this, in gate exam, many questions you will see they are connected between different subjects. All the nice questions that you will see, they are connected between different subjects. Okay, like in 2019 there was a question which has connected discrete mathematics plus TOC. So they were asking number of states in the minimal DFA, and they were asking some, they have given some bijection. Okay, so the answer, I think the answer was 120 or something. So you can see in gate exam they ask you this type of nice question where they will mix different subjects. So this was a nice problem in which we are using the concepts of different subjects, discrete mathematics and engineering mathematics. So that is the point. Now let's see the next question. He is saying that show that a finite simple graph with more than one vertex has at least two vertices with same degree. This is a very nice question, and this is a important theorem also. If you don't know this, then you should know, and we will also prove it very easily. You can prove it, but let's understand what he's saying. He's saying that if you have any simple graph, whatever simple graph you will see, whatever simple graph you can take, you will always see that there will be at least two vertices which have same degree. In this graph you can see it has degree 2, it has degree 1, degree 1. You can see this vertex and this vertex, they have same degree. So this is the theorem. He is saying that if you have a finite simple graph with more than one vertex, because of course if you have single vertex, then there is only one vertex, so you must have more than one vertex. In a simple graph with more than one vertex, you will definitely have at least two vertices with the same degree. Whatever you do, if you try to make it false, then you can try. For example, let's assume you have two vertices. If you do not connect them, then their degree is same. You can see this has degree 0, degree 0. Again we have two vertices of same degree. If you connect them, then again what we will do, we will get this degree 1, degree 1. So you can see again we have two vertices of same degree. Okay. Now let's assume you have three vertices A, B, C. You connect like this. Let's assume. Again you can see this has degree 2, degree 1, degree 1. Again this vertex and this vertex, they have same degree. So you will, if you connect like this, then what will happen? Now this has degree 2, this has degree 2, this has degree 2. Again you have at least two vertices of same degree. So this is the theorem that in any simple graph, in every simple graph, at least two vertices we will have which have same degree. Okay, so let's prove it, and we can prove it by pigeonhole principle. By pigeonhole principle we can prove it. This pigeonhole principle, I hope you already know. Let me revise it. Pigeonhole principle says that let's assume you have n pigeons, A, B, C, D. Let's assume you have four pigeons. Okay, four pigeons, and assume you have only three holes. So these pigeons, they are coming back to their homes. Okay, these three rooms you have, or you can say these three holes you have. Now, because you have four pigeon, now you will see that at least two pigeon will go to the same hole. At least two pigeon, definitely they will go to the same hole. Okay, for example, let's assume you put A here, you put B here, you put C here. Now where will you put D? So to put D, you will have to use one of these holes. Let's assume you put D here. You can see that at least two pigeons will go to the same hole. That is the point. So this is our pigeonhole principle. In pigeonhole principle, what happens? If your number of pigeons, let's assume this is your number of pigeons, this n pigeons you have, and let's assume n minus 1 holes you have, means there are more pigeons, there are less holes. In this situation, what will happen? At least two pigeon, at least two pigeon, at least two whatever pigeon will go to same hole. At least two pigeon will go to same hole. So this is a pigeonhole principle. Okay, let's try to see some easy examples on pigeonhole principle. For example, let's assume there is a room. In this room, let's assume you have 370 people. There are 370 people in this room. If you have 370 people in this room, then you can guarantee that at least two of them will have same birth date. So what I am saying, in this room you have 370 people, you can guarantee that at least two, means at least two people have same birth date, same birthday, same birthday they have. Okay, now you can very easily see, because there are 370 people, and in a year how many maximum days you have? You have 366. This is the maximum number of days you can have in a year. Okay, 366 days, this is the maximum you can have. If this is a leap year, then there will be 366 days. Anyway, you can see there are 370 people and there are only 366 days. So these are your pigeons. There are 370 pigeons and these are your holes, 366 holes. So what you can say? You can say that at least two people will go to the same hole. And what is hole? Hole means day. So at least two people will have same birthday. So that is the point. This is how you can very easily apply the pigeonhole principle. Now we will see this theorem and we will prove this theorem using pigeonhole principle. So this theorem is saying that if you have a finite simple graph with more than one vertex, then at least two vertices will have at least two vertices will have same degree. So let's prove it. Let's assume that our graph is connected. First, okay, we will take case one. In this case one, let's assume our graph is connected. If our graph is connected, then you can see that every vertex has degree at least, and also let's assume this n is the total number of vertices. This is greater than 1, because we are saying that at least more than one vertex you must have. So this n is greater than 1. Now, if our graph is connected, then what you can say? You can say that every vertex has degree at least 1. Okay. For n vertices, degree ranging from 0 to n minus 1, at least two vertices will have the same degree. So Sabrina, we are proving it. We are either our graph can be connected or our graph can be disconnected. Yes, of course, these two cases are possible. Either it will be connected or it will be disconnected. Now, if this is connected, then what will happen? Then every vertex will have at least 1 degree. So you can say that degree of Vi, this will be greater than or equal to 1. Every vertex will have at least 1 degree, because we cannot have 0 degree vertex. If this graph is connected, then 0 degree vertex is not possible. Are you getting this point? So that's why 0 degree vertex is not possible. Now, so this degree 1 is possible, degree 2 is possible. And what is the maximum degree that is possible? That will be n minus 1. This is the maximum degree that is possible. This maximum degree means when this vertex is connected to every other vertex. If this is the situation, then what will be the degree of this vertex? That will be n minus 1. So these are the possible degrees. These are our holes, because these are the possible degree. Either degree 1 vertex you can have, or degree 2 vertex, and so on, or degree n minus 1 vertex. But total how many vertices you have? Total n vertices. So these are the pigeons. N vertices you have. So you can see that you have n vertices and you have only n minus 1 holes. Total how many holes you have? Total 1 to n minus, that is only n minus 1 holes. You can say n minus 1 holes. So n minus 1 holes and n pigeons. So at least two vertices, at least two pigeons will go to the same hole, means at least two vertices will go to the same degree. At least two vertices, they will have the same degree. At least two vertices will go to the same hole. So that's why you can see in this case one, we have proven that at least two vertices will have same degree. Okay. Now let's prove case 2. After this case 1, let's prove case 2. In this case 2, let's assume our graph is disconnected. Means our graph is disconnected. If this is the situation, then what is the minimum degree? Of course, the minimum degree can be 0, because now our graph can be like this. Let's assume A, B, C, and D. You can see this is a disconnected graph, and this vertex has degree 0. So now our minimum degree is possible is 0. Now you can, what is the maximum degree possible? Can anyone tell me what is the maximum degree possible for any vertex? In a disconnected, you have a disconnected graph, then what is the maximum degree that is possible? Anyone want to tell me? So okay, let me tell you. See, this is a disconnected graph. So your vertex cannot have maximum degree n minus 1, because when do we have n minus 1 degree? Let's assume this vertex a you have, when it will have n minus 1, it will have n minus 1 when it is connected to every other vertex. When it is connected to every other vertex, then it will have n minus 1. But if this vertex is connected to every other vertex, then this graph is connected. This graph is not disconnected, because every two vertices have path. From this vertex you can go to this vertex via a. From any vertex you can go to any other vertex via a. So you can see that if your vertex has if any vertex has n minus 1 degree, then your graph cannot be disconnected. But we have a disconnected graph. What it means? It means that no vertex can have n minus 1 degree. So the maximum degree that is possible, that is n minus 2. In a disconnected graph, the maximum degree that a vertex can have, that is n minus 2. Okay, now these are your holes. And how many holes you have total? From 0 to n minus 1, total n minus 1 holes you have. Now how many pigeons you have? So how many pigeons you have total? N pigeons you have, because n vertices are there, right? Now again the same thing, n vertices, n minus 1, so n pigeons, n minus 1 holes. What you can say? You can say that at least two vertices will go to the same degree. At least two vertices will go to the same hole. So again we have, in this case too, we have that at least two vertices will have same degree. So now we have proven both the cases, case 1, case 2, both cases are covered. So this is how you can prove that if your graph has more than one vertex. So if you have a simple graph, uh, of number of vertices must be greater than one. Of course, at least two vertices must be there in your graph. Then at least two vertices will have same degree. At least two vertices. You can guarantee that at least two vertices will have same degree. Now we can. So this is the proof. You can just go through this proof. I have proven it. Okay, this is the same proof. The same idea is discussed in this proof also. But now let's solve this question. This is a nice question, very nice question. This is, in this question, what he is asking. This question is combination of DBMS, relational algebra. Like, okay, in DBMS we have something called we study something called relational algebra. So this is a question which connects relational algebra plus discrete mathematics. This is a combination of both these. Now what this question is saying, let me read it out. He's saying, for simple graph, first of all he's saying simple graph degree of vertices of graph are stored in a database table D of G. So he's saying that you have a graph G, and for that this graph G is a simple graph. He's saying that this is a simple graph, and he's saying that the degree of vertices, if you see the degree of vertices of this graph, they are stored in a table D degree of G. So this is a table you have. This is a relation you have. He's saying this table has two attributes, V comma D. So this is the table you have. This V represents the vertices, D represents the corresponding degree of those vertices. For example, if Vi is a vertex, okay, Vi is some vertex of degree Di, then you will have Vi comma Di. Basically, we are putting all the vertices and we are putting their degrees. Vi comma Di, V1 comma D2, and so on. V1 comma D1, V2 comma D2, and so on. Okay. He is saying that then there will be a row. Okay, yeah. So this is how we are making a table. So this is the relational table we are making from a graph. This is a simple graph. From this graph, we are making this relational table. We are basically storing the degree of vertices. We are putting all the vertices and we are putting their degrees. So this is how we are making a table. Now he's saying that v is the primary key. Of course, v is the primary key because we are putting all the vertices v1, v2, and so on. So of course, all these are unique. v1, v2, v3, v4. So that he has also given that v is the primary key in this table. Now he's saying that for a 20 vertices, means if you have in this G, if you have 20 vertices, then the summation of minimum and maximum possible value of this relational algebra query he has given. What is this relational algebra query? Let me tell you. First of all, he is saying that pi of d from deg of g. He's saying this is your projection. You can see this is in relation algebra, this is projection operator, and this is your table. This is deg of g. This is the table. This is the table. Now he's saying that what this query will do, relation in relational algebra, this query, what it will do, it will project this column will be projected, this attribute, this will be projected, means in the output you will have this attribute, this column you will have in the output. Now he is saying that what is the minimum and maximum cardinality of this. What is the minimum and maximum cardinality? Means how many minimum tuples you can have, how many maximum tuples you can have. Okay, let me very easily, let me just assume that you have a graph like this: a, b, c, and d. Let's assume this is your graph. Now in this graph he's saying that from this graph G we are making a table, and that table is this, and this table, the name of this table is deg of g. So this is your graph G. We are making a table, and what is this table? It has v and d. We are storing like vertex A has degree, this vertex has degree 2, this vertex has degree 1, this vertex has degree 2, this vertex has degree 1. So A has degree 2, B has degree 1, C has degree 2, D has degree 1. So this is your table. First of all, he is making this table. You can see in this table, you can very easily see this is the primary key because we have different vertices. This D cannot be the primary key because you can see we can have same values. But anyway, the point is this is how he is making a table. This is how he is storing degree of this vertex in a table. In a database, he is storing like this. Now, on this table, he is making a query on this table like this: pi d of deg of d. So from this table, he is projecting this attribute, this column. So if you execute this query, then what will happen? You will get the result will be like this. The result will be this 2, 1. So this will be the result. Okay, because you are projecting. And remember, in relational algebra, this will always have different tuples, different value. Like you will not have like this 2, 1, 2, 1. No, this you won't have. You will have unique values, unique tuples. No tuple will be repeated. So the result will be like this. On this table, if you execute this query, then the result will be 2, 1. This will be the result. Now he's saying that, and now he's asking what is the cardinality of this result. Like the cardinality of this result, that is 2, because you have two tuples. So the cardinality of this result is 2 because number of tuples is 2. Now this basically I have just made you understand the question, what this question is saying. Now in this question he is asking that assume you have a graph and this graph has 20 vertices. This is the only information we have, that this is a simple graph, and in this simple graph we have 20 vertices. Now from this information he is saying that if you execute this query pi of d from this d of g, okay, now then you calculate the number of tuples, so the what is the minimum value of it possible and what is the maximum value of it possible? Anyone want to answer? Anyone want to try? Take 1 minute. Try this. What is the minimum value possible? What is the maximum value possible? The only information that we have is that our graph is a simple graph with 20 vertices. This is the only information we have. So what is the minimum number of tuples possible? What is the maximum number of tuples possible in this query? Try this. So anyone want to try? So okay, let me tell you, like what will be the minimum? Minimum will be one, because what will happen when you will have one, if all the vertices have same degree, let's assume this, every vertex has same degree. Okay, in this G you have 20 vertices, and let's assume every vertex has degree 9. Let's assume this is a complete graph. This G is a complete graph. Then what will happen? Then basically every vertex has degree 19. Every vertex has degree 19, 19, 19. Okay, every vertex has degree 19. So in your table, what you will have like this: A has 19 degree, B has 19 degree, C has 19 degree, and so on. Basically every vertex has same degree. If you have this type of graph, in your graph, every vertex has same degree. Regular graph. This type of graph is called regular graph. In regular graph, every vertex has same degree. Okay, so if your every vertex, if you have 20 vertices and they all have same degree, 19, 19, 19, 19, and so on. Now if you project this column, you are projecting this column, then what will be the result? The result will be basically very simple. The result will be this. So there will be only one tuple. So you can say that the minimum will be one. And when it will happen? It will happen when you have a regular graph. Whatever regular graph you have. For example, you can have complete graph. Complete graph is also a regular graph. You can also have, for example, all the let's assume these 20 vertices, they are all isolated. A1, A2, A3. Let's assume all these 20 vertices are isolated. No one is connected. Everyone is isolated. Everyone has degree 0, 0, 0. In this case, what will happen? In this case, every vertex will have degree 0, 0, 0. Every vertex has degree 0. Finally, when you do this projection, then what you will get? You will get like this. You will get like this. So how many tuples you have? There is only one tuple. So you can say that the minimum number of tuples that you can get, that is one. When you have regular graph, in that case, you will get only one tuple. Okay. Now, what is the maximum tuples you can have? Maximum tuples you can have. So the maximum tuples. Now, some students might be thinking that maximum tuples will be 20 if every vertex has different degree. Okay, if every vertex has different degree, then what will happen? Every vertex has a different degree, different. Then 20 will be the answer. But we have already seen that in any simple graph, at least two vertices will have same degree. At least two vertices. So we can guarantee that at least two vertices will have same degree. We can guarantee this. Okay, so you have, let's assume you have 20 vertices, A1, A2, A3, and so on, A20. We have already seen that this is your vertex and this is degree. We have already seen that at least two vertices will have same degree. At least two vertices. Let's assume this has degree D, this has degree D. So at least two vertices will have same degree. Now if you project this D, then what will happen? If you project this D, you can see that because of these two vertices, only one tuple will come. So maximum, how many tuples you can get? You can get 19 tuples. This is the maximum number of tuples you can get. Because remember, in every simple in every simple graph, at least two vertices, they will always have same degree. At least two vertices. So that's why you can say at maximum 19 tuples you can get. So this is the answer. So maximum is 19 and minimum is 1. So the total will be 19 plus 1, that is 20. This will be the answer for this question. So this will be the answer for this question. You can very easily see. Okay. Now, Anyone has any doubt, then you can ask. So you can see this is a very nice question. I think this is a very nice question. In this question, he is mixing DBMS, relational algebra query, with graph theory. So this concept, if you know, this is a standard theorem. This is a very standard result, that in every simple graph, at least two vertices will have always same degree. At least two vertices, they will always have same degree. This is a standard concept. We have seen proof of it. Okay. Now, so basically this is like this. Now this is a nice question, I think, and these type of questions you will find in the gate exam. In the gate exam, what happens? Let me tell you. Let me tell you what happens in gate exam. Like, uh, in gate exam, you have total 100 marks. This is 100 marks paper. You only need 70 to 80. If you have more than 70 marks, more than 70 marks will guarantee that you will get top 100 rank. More than, so basically you can see more than 70 marks you need. But out of these 100 marks, almost you can say 45 to 50 marks are easy. These are easy, you can say. And remaining 50 marks are creative, very creative. So like these, almost these 50 marks, you will get these questions. 50 marks questions you will get from your standard thing, like from your notes you will get. Okay, from your notes you will get these questions. Like they will ask you, what is the time complexity of merge sort, what is the output of this scheduling algorithm. Okay, what is the tag size in paging, what is the tag size. So all the standard questions that we have, frequent questions, every year those questions are coming. One question on k-map they will ask. Okay, so you can see these standard questions. So these 50 marks will come, at least these 50 marks will come from standard previous year gate questions, you can say, pyq, directly from pyq. Just some data will be changed, or some you can say it will be framed in a different way, but the basic questions you will get. Okay, like one question you will get from mathematical logic, one question you will get from maybe fragmentation, ip addressing, and so on. That is the one question from tlb, cache memory, and so on. So standard questions you will get. So if you have already done previous year questions of gate exam very nicely, if you have already done, then if you have done it nicely, then you can definitely get these many marks. 50 marks you can definitely get. If anyone is not getting these 50 marks, then it means that they have not done this pyq nicely. Maybe they have just completed this pyq, but without like most of the things they have by hearted. Maybe they have not understood the concepts. They have not tried to understand the concept. They have just by hearted, like the previous question that we were taking. In that previous question, I told you, I have seen many students, they would, what they do, 10 vertices, so they will directly do, because they want maximum edges, so they will put one vertex here, 9 vertex here, then they will do 9c2. Of course it will save you a lot of time. It will save you a lot of time, but they don't know the concept, why they are doing this, why they are doing this 1,9. We have proven it. Once we have proven it, now you have some idea. Now you have some more idea, like how it is coming, because it is coming from here, a and 10 minus a. Then we are having an equation, a square minus 10a plus 45. This is the equation we are having. Then we are making it maxima minima. We are making it maximum, we are making it minimum. So those concepts we are applying, and after applying those concepts, finally we get the conclusion that a will be equal to a 1 or 9, either a equal to 1 or a equal to 9. So this is the conclusion that we get finally. So you can see those students, what they do, they directly do this. They have by hearted it. Now in gate exam, what they are going to do, the gate professor, the gate exam is the gate questions are made by the professors from iit, iisc. So those professors know this thing. They know that students directly by heart that, okay, put 1 here, 9 here. So they will change the question in such a way, they will make this question in such a way that if you do like this, then you will get the wrong answer. They will make some condition they can put. Maybe they can say that what will be the maximum number of edges. Like they can ask you this question, what will be the maximum number of possible edges is possible if you have at least four components. At least four components. So many conditions they can put. They know everything. So that is the reason So this is my observation. Every year I attempt gate exam, and this is my observation from gate exam, that these 50 questions, these 50 marks you can get from solving pyq nicely, and these remaining 50 questions are creative. Sorry, the remaining these 50 marks, these are creative. Here you need all your creativity. Here they will ask you combined question, like from discrete mathematics from toc. In the same question you need to apply the concept of toc, you need to apply the concept of discrete mathematics. Like in this question, in the previous question, in this question you can see, in this question you need to apply the concept of dbms, you can say dbms, that relational algebra, plus the concept of disk graph theory. So you can see, so these type of creative question they will ask you in the gate exam. These 50 marks, they will be from creative. Now you know that total you need only 70 marks. If you want top 100 rank, then you need 70 marks. So 50 marks you can get from here. And from out of these creative 50 marks, you only need 20 marks. You can see, you only need 20 marks. If you get out of these 50 creative marks, if you get 20 or 30 marks, then you will definitely get top 100 or top 50 or top 10. So that is the point. Out of these creative marks, only these many marks you need. But many students, you will see that they get this these many, like from 40 to you can say 55, in this range, 40 marks, from 40 marks to 55 marks. In this range many students are there, many, a lot of students are there. Okay, because of these marks, these 50 marks everyone will get. Everyone who has done previous year questions nicely, only this much effort if you have put, then you will get these many marks. So that's why many students get these many marks. But the toppers, what they do, they get these extra marks. These are the extra marks that they get. From these creative marks, they get 20 or 30 marks, and then they get top 100 rank. So this is how you should also like do. Anyway, all the creative questions you must respect, and you should appreciate those questions. You should solve those questions, and you should try to think, like, okay, how to solve this question, how to analyze this question, what will happen if instead of this is happening, and so on. So these type of things you need to do. Then you will get these extra marks, and these extra marks will make the difference between toppers, between the top 100 rankers and between the top 1500 rankers. So that is the difference that will happen because of these extra marks. Okay, if there is a easy question, if there is any easy question, then everyone is going to get it. Okay, anyway, so let's see the next concept. Okay, let's see the next concept. And okay, Sabrina, I don't know. Anyway, so yeah, so the next concept that we will see is this: what is a independent set and many things. Okay, so I will just give you the idea. Like, we have some numbers associated with any graph. If you have any graph G, whatever graph you have, for example a b, let's assume I am taking a graph G like this, a b c d. Assume that this is your graph. In this graph you have some numbers associated with this graph. First is independent set. Independent set. What is this independent set? Independent set means a set of vertices which are not adjacent. For example, you can say that this a and b, these are adjacent because we have edge between a and b. So we say that this a and b, they are neighbors. Or you can say this a and b, they are adjacent. D comma, you can say this is your c. D comma c, they are adjacent. B comma c, they are adjacent. You can see a comma c, they are not neighbors. A comma c, they are non-adjacent. A comma b. Similarly, a comma e, they are non-adjacent. B comma e, they are non-adjacent. So independent set means a set of vertices, a set of vertices who are independent of each other. Independent of each other means basically they don't know each other, or you can say they are not neighbors. For example, you can say that this a comma e, this is independent set, because you can see each vertex is independent of other, or you can say each vertex is non-adjacent to other vertex, like this a comma e. Similarly, you can see this a comma c, this is also independent set. B comma c, this is not independent set because b and c, they are adjacent. So that's why this b comma c, this is not independent set. For example, a comma c comma e, this is not independent set. Why? Because you can see this a is non-adjacent to c, but c is adjacent to e. Independent set means set of vertices which are pairwise non-adjacent, means no one is adjacent to any other vertex. Okay, pairwise non-adjacent, collection of independent vertices, collection of non-adjacent vertices. That is the point. Now you can see this is independent set, this is independent set. What is the maximum cardinality independent set? Like, what is the maximum independent set I can make? So the maximum independent set that I can make, you can see, that will be of size only 2, because either I can make a comma e, or I can make a comma c, or I can make b comma e, but you can see I cannot have 3 vertices. So this is the maximum size of independent set, that is 2, either this or b comma e. You can see b comma e. So you can see this is the maximum size of independent set that is possible. This is called maximum independent set. Okay, or you can say this is independence number. This 2 is basically independence number. So this is independence number, and that is equal to 2, because, so this is the definition of independence number, that independence number means the cardinality of maximum independent set. Whatever maximum independent set you can make, remember, this is also independent set. Okay, also, like, this is also independent set. Independent set means there is no pair of vertices is adjacent. So you can see this is also independent set, this is also independent set, but these are not maximum cardinality independent set. The maximum cardinality independent set is this. So independence number will be 2. This is the concept of independent set. Now they can make some creative questions. Like, let's take this example: b d. Right. Okay, yes. A, B, C, D, E. Yes. Correct. So here you can see this BDE. This is also independent set. BDE. This BDE. This is also independent set. Hence the max. This is maximum independent set. So the independence number will be 3. Yes. Sorry. So in this graph you can, okay. So in this graph you can see this B comma D comma E. This is the maximum independent set. You can see, and so the so the independence number will be 3. This is the independence number. You can see this B is non-adjacent to D, this D is non-adjacent to E, this E is non-adjacent to B. So that's why this is independent set, and this is the maximum independent set that we can make. So hence the independence number will be 3. Okay, now let's see some questions. Assume you have a bipartite graph. You have a complete bipartite graph. Here you have 10 vertices, here you have 8 vertices. Okay, and this is a complete bipartite graph. Means this is basically K10, 8. Complete bipartite graph means what happens? Basically, complete bipartite graph is like this. Here you have some vertices M, here you have some vertices N, and you have edges between these two partitions. So these are partitions, and you have all the edges possible that are between these partitions. Means every vertex here is connected to every vertex here. So this is called this is called, you can say, complete bipartite graph. Now assume that you have a complete bipartite graph K10, 8. Okay, all the let me just tell you all these concepts, like bipartite graph, all these graph theory concepts, all these basic concepts, everything we have already seen in the GATEFORUM discrete mathematics course. There we have already seen all these basic concepts. Today I am only taking some tricky examples, some tricky concepts, some more you can say some mixed concepts, or some nice questions I am taking. So that is my purpose of today's class. Okay, now let's see this question. So you have a complete bipartite graph, then what will be the maximum independent set? Tell me, what is the independence number? Basically, what is the independence number? Tell me, what will be the independence number? So so the independence number will be basically very easily you can see every vertex here, like this vertex, this is connected to every other vertex. Similarly, this vertex is connected to every other vertex. Similarly, this vertex is connected to every and so on. So independent set you want. So what you can do very easily, you can do like this. If you take all these 10 vertices, you take all these 10 vertices, okay, then you can see they are non-adjacent because there is no edge between these in this partition. Within this partition there is no edge. If you see this partition, then there is no edge within this partition. So what you can say, you can say that if you take all these 10 vertices from here, then they will make an independent set. Similarly, so this is an independent set. Similarly, if you take this partition, all these 8 vertices, they will also make independent set because there is no edge within this partition. In a bipartite graph, within a partition, you never have any edge. So that's why within this partition, there is no edge. Hence, you can say that, but remember, this is bigger independent set. This has 10 vertices, this has 8 vertices. So this is bigger independent set. Hence, you can say that the answer will be basically 10. Okay, so or you can say simply you can say maximum of m comma n. If m vertices are in one partition, n vertices in another partition, then you will have maximum of m comma n. These many will be this will be the independence number in a complete bipartite graph. Now in GATE exam, what they can do, they can ask you some tricky questions. Like they will do like this. Assume you have a complete bipartite graph where 10 vertices here and 8 vertices here. This is a complete bipartite graph G. So this G is complete bipartite graph K10, 8. Now what they will do from this G, they will make G dash. In this G dash, what they will do, they will add edge in this partition. Like in this partition, they will add an edge. Means vertex A, vertex B. Between these vertices, they will add an edge. Means basically you can say G plus E. G plus E. In this graph, they will add one edge, extra one edge. Let's assume this edge they are adding in this partition 10. In this side, they are adding this edge. Now in this G dash, what will be the independence number? Anyone want to try? In this G dash, what will be the independence number? Like these type of tricky questions, these type of variations they can ask. Small variations they can ask. So now what will be the independence number? Anyone want to try? Right. So now you can very easily see, now the independence number will be 9. Okay. The independence number now will be 9 because you can see this vertex, let's assume A comma B, these two vertices are connected. So now you cannot take all these 10 vertices. Okay. What you will have to either leave out A or you have to leave out B. One of them you will have to leave out. So you can take 9 vertices. Okay, the remaining 8 vertices you can take, and either A you can take or B you can take, either this or this. So you will see that total 9 will be there. Now in the same question, let's assume they add an edge in this partition A, B. Let's assume they do like this. They add edge here. Now what will be the independence number? Tell me. Basically what they are doing in this complete bipartite graph, they are adding this edge, but this edge that they are adding this edge in this partition, in this smaller partition they are adding this edge. Now what will be the independence number? You can see the answer will be very easily, answer is still now will be 10 because now you can again take these all these 10 vertices, these all these 10 vertices you can again take. Okay, so that's why now the answer will be 10. These small variations, very small variations they can ask. Now let's see another variation we can ask. Let me ask you another variation. Assume that you have a k 10 comma 8. In this they are adding two edges. Let's assume they are adding two edges. We don't know where they are adding, where they are adding these two edges. We don't know. They are adding two edges, and this they are calling g dash. Now what are the possible independence numbers of g dash? What are the different possible independence numbers? Possible independence numbers, like what are the possible independence numbers of g dash? Try this question. Remember, in this graph they are adding two edges, but we don't know where they are adding these two edges, whether in the bigger partition or whether in the smaller partition, or whether in one in bigger partition, another in smaller partition. So you can see there will be three cases. So he is asking what are the possible independence numbers. Let's see. So here they are adding two edges. Now one case one is this. Okay, here 10 vertices, here 8 vertices. Let's assume both edges are added here. If both edges are added here, then the answer will be 10, because this bigger part you can take. In case 2, let's assume that in this bigger part they are adding two edges. But again there are two cases. Again here there are two cases, and one case is, so in the bigger part, if they are adding two edges, then either they can do like this: AB they are adding edge, and CD they are adding edge. So this is one possible case. And here we have 8 vertices. So here we have 10 vertices, here we have 8 vertices. So this AB edge, this CD edge, two edges we are adding. Now in this case, what will be the independence number? In this case you can very easily see, because you cannot take A comma B, you will have to take one of them. Similarly, you cannot take C comma D, you will have to take one of them. You will have to leave out one of them. So you can see, from if you take 8, so basically the 8 will be the independence number. Okay, this 8, this will be the independence number, because you cannot take A comma B both. You will have to leave out one of them. Similarly, you will have to leave out one of C comma D, one of them you will have to leave out. So that's why this will be the answer. But remember, there is another case possible. What is that another case? Like this is A, this is B, and these two edges are like this: A, B, C. These two edges that you are connecting, these two edges you are putting like this. Now what will happen? Now the answer will be 9, because you cannot take A comma B comma C all of them together. But what you can do, you can remove B. You can remove B. You can see, remember, A and C, they are not adjacent. So you can remove B. If you remove B, then still you have 9 vertices. So the independence number will be 9. So this 8 is also possible, this 9 is also possible in this case. So you can see in this case, when you are putting two edges here, both the two edges E1 comma E2, when you are putting here, then there are two possible: 8 comma 9. These are possible. Okay. Now what is the case 3? In case 3, you can put one edge here, A comma B, and another edge here, C comma D. This is another case possible. In this case, you can very easily see the answer will be still 9. So the answer will be still 9. Okay, because you can take the bigger part, but from this bigger part you will have to leave out either A or B. One of them you will have to leave out. So you can say that 9. So these are the possible independence numbers. What all the cases we have considered, every case we have considered. So you can see either 10 or 8 or 9 or 9. So these are the independence number that are possible, either 8 or 9 or 10. Okay. So this is how you can basically solve these variations. So anyway, hopefully you got these small variations. They can always ask. You should also, when you are studying, when you are learning some concept, you should also make your own variations. Sometimes you should try, okay, making your own variations, and then try to solve it on your own. Like, it's not like you are making your own variation and then you are asking someone else. No, if you are making your own variation, then you should put your best effort to solve it. Okay, so anyway, that is the point. Now let's see the next concept after this independent set. Now let's see the concept of matching. This concept of matching, this is similar to independent set concept. But in independent set, what we have set of vertices which are independent of each other. And in this matching, what we have set of edges which are independent of each other. Now what is the independent edges? For example, let's assume a comma b comma c comma d. Let's assume this is your graph. In this graph, you can see we have four edges: E1, E2, E3, E4. If you see, one thing you can notice that this E1 and E2, these are neighboring edges. These are adjacent edges. E1, comma E2, these are adjacent. Why these are adjacent? Because they are sharing a common point, common endpoint. This E1 is incident on A, this E2 is incident on A. So they are sharing a common endpoint. This is the common endpoint of E1, comma E2. So we can say E1 and E2, these are adjacent. Similarly, you can say that E3, comma E4, these are adjacent. You can also say E1, comma E3, these are also adjacent. E1, comma E3, they are also sharing the common endpoint. But what about E1, comma E4? You can see these are not adjacent. These are not adjacent because even the endpoint of E1 is A, comma B, and endpoint of E4 is D, comma C. So you can see there is no common endpoint between E1, comma E4. So these are non-adjacent edges. This is the concept of non-adjacent edges. Now you can very easily see what is this matching. This is similar to independent set, but in the independent set concept, we are making set of vertices which are non-adjacent. Here what we will do, we will make set of edges which are not non-adjacent. So you can say edges set of edges which are pairwise non-adjacent. Means every pair of edges that must be non-adjacent. So pairwise non-adjacent. So this is a simple definition. So now let's see some questions on matching. But remember one thing, that this matching is in terms of edges. So sometimes what we have like this, in terms of edges, this concept is defined in terms of edges, and these are the concepts that are defined in terms of vertices. For example, this independent set, this concept is defined in terms of vertices, and this concept is defined in terms of edges, but they are similar concept. Here we are taking set of vertices which are non-adjacent. Here we are taking set of edges which are non-adjacent. Similarly, you also have some different concepts. For example, we have vertex coloring, and here we have edge coloring. So this coloring concept, again, this is defined in terms of edges and vertices. So vertex coloring and edge coloring. On this edge coloring in 2020, there is a question on edge coloring. So you can see this. Similarly, we have some more concept. For example, we have a concept of vertex cover. We have concept of vertex cover. Okay, and here we have something, a concept of edge cover. So you can see this is concept of edge covering, and this is the concept of vertex covering. So basically in terms of vertices, if you are defining a concept, then similar concept you can define in terms of edges. Okay, and these concepts are more popular, like matching, comma independent set coloring. These concept, and also this vertex cover, these concepts are more popular. So we have already seen this concept. Now let's look at this matching. So this concept matching, this is easy, just set of edges which are non-adjacent. Now let's take more examples. So assume that you have a complete graph. Okay, let's assume this is a complete graph on four vertices. So this is your complete graph, A, B, C, D. In this complete graph, you can very easily see that what is the matching. For example, you can very easily see this AC, this is matching. There is only, if I take only this age, AC, this age, if I take, then you can see this is a matching. You can see that this AC comma CB, this is not a matching, because they are sharing common endpoint. AC, CB, they are sharing common endpoint. Very easily you can see, because when you write AC, CB, you can see they are sharing common endpoint. So that's why this is not a matching. You can very easily see that this AC comma BD, this is a matching. You can see they are not sharing any common endpoint. Here we have A comma C, these are the endpoint. Here B comma D, these are the endpoint. So this is a matching. In this complete graph, you can very easily see, this is a complete graph on 4 vertices. In this, you can see that the maximum matching that you can make, that is only of size 2. Okay, because this is the maximum matching you can take. You can take AC, you can take BD. Now all the vertices are covered. Every vertex is covered. A is covered, C is covered, B is covered, D is covered. So all the vertices are already covered. Now you cannot take any other edge. Whatever edge you take extra, that that will again be adjacent to one of these edges, because already all the vertices are covered. So this is how you can see. This is the matching concept. Moreover, this is called perfect matching. Perfect matching means a matching which covers all the vertices. So this type of matching is called perfect matching. For example, this is not a perfect matching. Here we are only covering A comma C. This vertex and this vertex, they are covered. But this is not a perfect matching. This is a perfect matching, because every vertex is covered. Now, can we say that a perfect matching will always exist? No. Consider this example, A, B, C. This is your K3, complete graph on 3 vertices, K3. In this graph, you can see that we don't have perfect matching. Of course, we can have matching. For example, this is a matching, A comma C, this is a matching. Okay. For example, AB, this edge. Remember, this only one edge. This is also one edge. This is also a matching. But can you have perfect matching? No, you cannot have, because if you consider, if you want to cover all the vertices, you want to cover all the vertices. Let's assume you are covering A comma B. Now you are covering A comma B. After this, how can you cover this C? If you want to cover this C, then either you have to take AC or you have to take BC. But you can see, if you take AC, then they are no, these are sharing common endpoints. So these edges are adjacent, but this is not allowed. So this is not a matching at all. This is not at all a matching. Similarly, if you take BC, then again a common endpoint. So again, this is not a matching. So this is how you can see that sometimes perfect matching exists, sometimes it doesn't. Okay. So this is the concept of matching, concept of maximum matching. In this graph, the maximum matching will be of size 1. Size 1. This is the only one edge you can take. You cannot even take 2 edges, only one edge you can take. So this is the maximum matching that is possible. So the size of maximum matching, that is 1, and perfect matching is not possible. Now let's take, this is a gate question actually. I think gate 2006 six question we have. In this question he is asking, let's assume you have K6, complete graph on 6 vertices. Then how many perfect matchings you can make? This is a gate question. Gate 2006 or 2003 questions you can check, either 6 or 3. But anyway, he is asking that you have a K6 complete graph on 6 vertices. How many perfect matching you can make? How many perfect matching you can make? So you can try to solve this question, but okay, let me solve it. See, first of all, this is a complete graph. So what it means? It means that between every pair of vertices, you have edge. Okay, 6 vertices, you have A, B, C, D, E, F. Let's assume these are the 6 vertices. So between every pair of vertices, you have edge. Every vertex is connected to every other vertex. Okay, so this is your complete graph, like this. Okay, every vertex is connected to every other vertex. He is asking how many perfect matching are possible. So like this is one possible perfect matching. You take AB, you take CD, you take EF. So this is one possible perfect matching. You can see every vertex is covered. Okay, similarly you can see, you can take AB, you can take CF, you can take ED. So this is also perfect matching, and so on. So how many perfect matching are possible, he is asking, number of perfect matching. So very easily you can solve it, because okay, let's solve it by the product rule of combinatorics. In combinatorics we have a product rule. This is the basic counting rule. This is a this is a very basic counting principle that we have. Let's use it. This basic principle we will use. So you have six vertices, a b c d e f, and your target, your task, what is your task? Your task is to create a perfect matching. That is your task, perfect matching. This is the task. If you want to create a perfect matching, then what you know that this a must be connected to, because this a must be covered. Perfect matching means every vertex must be covered. So this a must be covered means with this a you must have something. Now this is a complete graph, so this a is connected to every other vertex. So you have five possibility. You can take any of these, either b or c or d or e or f. So how many possibilities you have? Total five possibilities you have. Five ways. You can take ab, you can take ac, or you can take ad, and so on. So five ways you have. Now you can see that, let's assume let's assume you are taking d. Let's assume you are taking d means with this a you are taking d. Anyway, there are five ways, but one of these five ways is you are taking d. Now you can see a is covered, d is covered. Once this has been done, now how many remaining vertices you need to cover? You need to cover b c e f. So because this is a perfect matching, so you need to cover b. Now to cover b, you can only use these three vertices, c, e, f. These are the three ways that are possible. So for this b, how many ways are possible? Only three ways are possible. Now assume that out of these three ways, assume that you are taking e. So this b, e you are taking. Now a is covered, d is covered, b is covered, e is covered. The remaining vertex is c. So it has to be covered by f. There is no way. There is only one way. There is only one way. Now you can see that. So your task is to make perfect matching, and to do this task, what you can say? You can say that you have divided this task into some subtask. Like you need to connect a, you need to cover a, you need to cover b, and so like this. So this is the point. Okay. Now you have to do this, and you have to do this, and you have to do this. So there is an and here. So that's why you can say five ways multiplied by three ways multiplied by one way. So the answer will be 5 into 3 into 1. So the answer will be 15. So the basic product rule, the basic counting principle we have used, and the answer will be 15. This is how very easily you can answer this type of question. Okay, they can ask you for any number of vertices. They can ask you, if they ask you, for example, let's assume in k8, in the complete graph on 8 vertices, how many will be there? How many perfect matching will be there? So that will be 7 multiplied by 5 multiplied by 3 multiplied by 1. So this will be the answer. In k8, these many will be the number of perfect matching possible, because for vertex a you have 7 ways. Okay, then for next vertex you only have 5 ways, and so on. So this is the answer. This is how you can solve. Okay. So this is the concept of matching and the concept of independent set. These concepts we have seen, and we will, in the next class we will see the remaining concepts like vertex cover and coloring. So these concepts are important: vertex cover, coloring, and also some cut set vertex, some cut set. This concept we will see. And what is this cut set? Okay. This is also defined in both in terms of edges, also in terms of uh, vertices. For example, this cut set, this can be defined in terms of vertex cut. So you can say vertex cut, or you can say edge cut. So again, these concepts are also there. Okay, so we have 5 minutes. Let me define this cut set. Let me define this cut set. This, in this cut set we have, either you can define it in terms of vertices, or you can define it in terms of edges. Let's see. First we will see in terms of vertices, means we will see vertex cut. What is this vertex cut? This is very simple. You have a graph. Let's assume this is your graph: a, b, c, d, e, and let's assume f. So you have this graph. In this graph, what is a vertex cut? Vertex cut is any set of vertices which will increase the number of components. That is the definition. So basically, cut set, vertex cut means set of vertices, you can say vertices set of vertices whose removal, if you remove those vertices, whose removal will increase the number of components, will increase the number of components. You can see right now this graph has only one component. This is a connected graph, so there is only one component. Now if I remove f, let's see whether this f is a cut set or not. If I remove this f, then what will happen? After removing this f, still there is only one component, so this f is not a cut set, because cut set means set of vertices whose removal will increase the number of components. This is the definition of vertex cut. So f, this is not a vertex cut. This set of vertex, this is not a vertex cut, because if you remove f, then still you right now you have one component. After removal of f, still you have one component. So that's why this is not a vertex cut. Let's see whether this e is a vertex cut or not. This e is a vertex cut, yes, because if you remove this e, removal of this e, you can see this is one component and this is another component. Okay, this will become disconnected, so the number of component will increase. That is the point. Number of component will increase because right now you have only one component. If you remove e, then number of component will become 2, so there is an increment from 1 to 2. The number of component will increase, so that's why this is a cut set. For example, in this original graph G, this C comma E, this is also a cut set. If you remove C comma E, you remove C, you remove E, then what will happen? This will be one component, this will be another component, this will be another. Total 3 component will be there. Right now you have one component, but after removal of these 2 vertices, you will have 3 components. So that's why again there is a increment in the number of components. So you can say this is also a vertex cut. Okay. Many times what they will ask you minimum vertex cut. Minimum vertex cut, like minimum how many vertices you need to cut so that you can increase the number of components. So here the answer will be 1, because if you remove this e, automatically you will increase the number of components. So that's why minimum vertex cut. So in this vertex cut, what they ask what is the minimum vertex cut. Minimum vertex cut means the minimum set of vertices whose removal will increase the number of components. Let's take an example. Let's assume this is example A, B, C, D, E. Let's assume you have this graph. In this graph right now you can see the number of components is 1 right now in this G. Number of components is 1 right now, one component. Okay. In this graph, what is the minimum vertex cut? You can see in this graph, this for example, this is not a vertex cut, because if you remove C, then the number of components will remain the same. The number of components will not increase. So this is not a vertex cut. But you can see this A comma E, this is a vertex cut. If you remove A comma E, if you remove this part, then there will be 3 component. This will be 3 component you will have. So this is a vertex cut, but we are interested in minimum vertex cut. You can see this is a minimum vertex cut. This itself is, this A is enough. If you remove this A, what will happen? After removing this A, this will be one component, this will be one component, this will be one component, and this will be one component. So after removal of A, there will be 4 component. Right now you have one component. After removal of A, there will be 4 components. So again, there is an increment in the number of components. So you can say this is a vertex cut and this is our minimum vertex cut. So the size of minimum vertex cut is 1. Okay. So this is how you can solve the questions of minimum vertex cut, or you can say vertex cut. Similarly, we can define edge cut. In a similar manner you can define edge cut. Edge cut means set of edges, e1, e2, and so on, set of edges whose removal will will increase the number of components. For example, consider this graph A, B, C, D. Consider this graph. Let's assume this is your graph. Now in this graph, You can see this is age E1, E2, E3. Let's assume this is age E3 and this is age E4. You can see that this age E3, this is not a age cut, because if you remove E3, if I remove this E3, you can see still this graph, still the number of components is the same. The number of components is still same. Earlier in the original graph, you have only one component. After removing this E3, also you have only one component. So you can say this is not a edge cut. So what is edge cut? This even is edge cut, because instead of this E3, if you remove this E1, if you remove this E1, then after removing this E1, this will be one component and this will be another component. So the number of component will increase. So this is edge cut. Okay. So this is how you can define the edge cut, very similar to the vertex cut. Now, for example, if you have a cycle, let's assume A, B, C, D. If you have this cycle, in this cycle, what is the minimum edge cut? You can see you don't have one size edge cut. For example, if you take this edge E1, E2, E3, E4, any edge you take, for example, if you remove E1, then still the number of component will be same. If you remove E2, still the number of component will be same. So you don't have one size edge cut. You don't have that. Okay. So the minimum edge cut will be more than one. So what you can do, maybe you can remove E1 comma E2. If you remove E1 comma E2, now what will happen? So you are removing E1 and you are removing E2. Now you can see this will be one component and this will be another component. So the number of component will increase. So this is your so this is your edge cut. This is edge cut EC. And so you can say that the size of minimum edge cut will be 2. This is the size of minimum edge cut. Okay. Or you can say edge cut number. Edge cut number, you can say that is 2. Edge cut number means the size of minimum edge cut. Similarly, vertex cut number means the size of minimum vertex cut. So these are the concept of cut set. Cut set is defined in terms of vertices. It is defined in terms of edges. If it is defined in terms of vertices, then we will call it vertex cut. If it is defined in terms of edges, then we will call it edge cut. So this is the concept of edge cut and vertex cut. Remember, the number of components must increase. If the number of component is not increasing, then that is not a cut. Cut means number of components must increase. That is the point. Okay. So the remaining concept, two concepts are remaining. One is vertex cover, edge cover, and edge coloring, vertex coloring. Basically, this cover and coloring. These two concepts are remaining. So we will see these concepts in the next live session. And also let me tell you that this complete discrete mathematics course, from the beginning, from the scratch, like very scratch, from the very basics to the you can say high level. So from the scratch to high level, all these concepts, all the complete this discrete mathematics course we have already studied in our GATEFORUM course. So if you want to learn this discrete mathematics, then very easily you can learn it. Okay, so you can enroll in the GATEFORUM course and you can study this discrete mathematics from there. Okay, we have already studied this complete course. In these live session, I am just taking some hard questions, you can say some tricky questions. Okay, some creative questions. That is my target in these live sessions. Okay, so in the previous live sessions also I have taken some hard concepts. For example, this model concept we have seen in the last class. Okay, before that also we have seen some tricky concepts we have seen in this today's class. Also we have seen this question. I think many questions in today's class were also tricky. Okay, like there was this question, DBMS plus discrete mathematics, the combined question, relational algebra plus graph theory. So these type of questions I wanted to discuss. And this number of perfect matching, that is a gate question. How many number of perfect matching are possible? That is a gate 2003 question. You can check it out. So okay, all these things we have seen. In the next lecture we will do this covering or coloring, and yes, this clique also we will see. So these concepts we will see in the next class. And if we will have some enough time, then we can start some new topic. Maybe we can start set theory or group theory, something. Okay. Okay, everyone. If you have any doubt, then you can always ask. Okay. Thank you.